Okay, we're going to continue on here. We started talking about transition metals last time. And again, we're talking about transition metals a little bit here in this chapter because the main focus of this chapter is going to be complex ions and also what's now referred to as coordination compounds. And a lot of times the sort of central metal in those guys are these transition metals. So we didn't get too far into it, I think, but again, a reminder that we do find our transition metals really between group 2 and group 3 on the periodic table. Also, technically speaking, those couple rows at the bottom really do go kind of like right in that spot there. And they are also sometimes referred to as intertransition metals, but most of the time we do focus on these guys between group 2 and group 3 on the periodic table. A lot of these guys down here are more radioactive type of elements that we come across when we talk about nuclear chemistry. But a lot of our complex ions will have some of those transition metals that are here. As we talked about, transition metals typically can have a variable type of charge, which is why we do use like Roman numerals, for example, again, when we name metals or ionic compounds that have transition metals in it. There are, again, 3 sort of exceptions to that, and zinc and cadmium, again, do have fixed charges of +2 when they do form a charge, and silver has a fixed charge of +1. But again, everybody else really in the transition metal region will have a variable charge. It will depend on who they're attached to, how many they're attached to, and that's pretty far as we got, I think. So I think where we left off, we were going to talk about now sort of electron configuration. And for transition metals, they are a little bit different. And hopefully remember how to write electron configuration. A reminder that you can pretty much, if you remember that on the first energy level, there's where S's orbitals appear. On the second is where P's. On the third is where D's appear. On the fourth energy level is where F's first start to appear. And then you pretty much can just fill in the numbers underneath each of these to give you the proper electron configuration order, except you should use the right letter would be great. Well, try that again with S's maybe. There we go. So 2S, 3S, 4S, 5S, 6S, and 7S. And then these would be my P's, 3P, 4P, 5P, 6P, 7P, 3D, 4D, 5D, 6D, and 5F there. And this is the order, as you probably saw something similar to this, I imagine, in Chem 50. You basically follow the arrows. And the major sort of difference is right around here, and that is the 4s orbitals are actually lower than the 3d orbitals when electrons are being filled into the atom. So they do go into there first. And we could write something like, for example, iron, which is 26. It'd be 1s2, 2s2, 2p6, 3s2, 3p6. Again, the 4s would come next, which would be 4s2, and 3d6. We also could use shorthand, as you are aware of, I'm assuming. And again, if we look up to about here and count the numbers that are up on top, that is 18 electrons, which on the periodic table is argon, right? So that is the electron configuration for argon. And you could do sort of the noble gas configuration, sometimes referred to, write an electron configuration like that, where the brackets indicate the electron configuration for argon. And then obviously you continue on there. That is what we see here for V, our argon 4s2, 3d5. There are a couple of exceptions to sort of the normal filling order, especially for transition metals. And the 2 major ones that most of the time people in Chem 50 sort of talk about is chromium and copper. chromium being 24 electrons and copper being 29 electrons. And it's been found experimentally that they are more stable with one extra electron up in the d orbital, one less electron in the s orbital. And they're able to do that really because these orbitals are pretty close to each other in terms of energy. So what actually happens is, as you're probably aware of, as the electrons go into the s orbital and then start filling the d orbital, that is the order of filling. There's actually a switch in energy that occurs once you start populating the d orbitals, and the 4s ends up being higher in energy than the 3d. And that is also important for how transition metals lose electrons when they become positively charged. So they will typically lose the highest energy electrons, which is actually the s electrons there, because of that switch in energy that occurs. If they need to, they then would dip into basically those d orbitals to fill in any more of a charge. But the two sort of exceptions there was just chromium, again, has an extra sort of electron up there in our d orbital. And again, that will sort of fill up the d orbital, all with parallel spin, which is a most stable arrangement. Hund's rule, right? Maximize parallel spin as you put those electrons in there. For copper, it also have one more up there that will sort of pair off the electrons there in the d orbitals. Now, you might also learn that on the periodic table, there's a lot of very similar exceptions to how electron configuration is written. And if you really look on the periodic table, really below chromium and below copper, things like silver and PD and those guys, there's also very similar sort of exceptions that occur. For example, like PD, for example, has maybe no electrons in the s orbital. They've all been promoted up to the d orbital and things like that. But most of the time, most people focus in on chromium and copper in terms of those exceptions. Any questions on that there? Speaking of which, as I mentioned, when they do lose electrons, unlike representative metals, which will lose electrons, and those are guys in group 1, group 2, and group 3 on the periodic table, when they lose electrons, they back up to the noble gas configuration that comes before them. Transition metals will not get there because they're losing the s's and they got all those d electrons they would have to kind of lose to get back to a noble gas configuration, but they do lose those electrons first. So that's what we see here in our TI and our TI3+. What's going to happen is, again, it's going to actually lose these 2 electrons here, and then it will need to dip into there to lose the 3rd electron. That is what the positive 3 represents, right? That it lost 3 electrons, and this would give us our proper configuration. So why don't you write the electron configuration for iron +3? And why don't you do like nickel 4? Let's see what you got. Iron's atomic number is 26. Nickel's atomic number is 28. All right. All right, let's take a look. So we'll start with the iron. So iron's 26 to begin with. So iron with, again, no charge. As I put up there, should be an argon 4s2 3d6. Again, with a +3 charge, it will lose 3 electrons. Once again, it's going to be these 2 that come off first, and that always happens with transition metals, the s's. But we still also need to kind of get into that guy there, and that would leave us with an argon 3d5. Yeah. Questions on that one there? Coming to nickel, which is 28. So nickel with no charge would be an argon 4s2 3d8. Here with a +4 charge means that it lost 4 electrons. So Once again, because it's transition metal, it is going to lose these two first. We then would have to come into here and take out 2 more to get the 4, and that would leave us an argon 3d6 should be left over. Question on electron configuration there. So it's important to know how to do this. A little later on, we're going to talk about sort of how electrons will be distributed with these metals. So you need to really know kind of how many d electrons these guys would have. So let's talk a little about oxidation states of the first row transition metals, and that's basically our 21 through 30-ish, a little less 30, 29. And we see there's a lot of different oxidation states. For example, Mn, which we did with our redox experiment, as you saw on that list, and maybe you saw in your experiment, it could have multiple sort of oxidation states. Most common ones here are in red, and for a lot of it, 2s and 3s are very common sort of oxidation states that a lot of these guys have. Sort of builds up in terms of oxidation state to the middle, and then kind of comes back down on the other side. Again, that +2, +3, very common, but it can have things like +7, like we see in Mn. Also +6 in chromium is very common as well. Now, ionization energy, when we talk about ionization energy, that is the amount of energy that's required, right, to remove an electron from the gas phase of an atom. That's basically what happens when we do a little cation formation, right? That is how you make a cation, is to remove an electron. The general trend of electronegativity I'm sorry, not electronegativity, but ionization energy on the periodic table is as you go up and to the right, it increases. And as you go down and to the left, it decreases. So things that are further up to the right, like our nonmetals, have very high ionization energy, which is why they typically do not lose electrons. It takes a lot of energy to try to pry an electron away from them. Left and down, which is basically metals, are guys that typically will lose electrons. They have less ionization energy, which means it's a little bit happier, a little bit easier, as opposed to a better way of saying that. A little bit easier to remove an electron. Now, electrons actually do come off one at a time. So kind of like hydrogens and all of those other things we've been talking about. When something loses an electron, it actually is sort of lost in a stepwise fashion. So, for example, if we take something like our friend magnesium, and when it loses an electron, the first thing that would happen is magnesium would pretty much lose 1 electron and become Mg plus an electron. There is a certain amount of energy required to do that, and sometimes referred to as ionization energy number 1, the first ionization energy, basically. Then what would happen is that guy that has lost 1 electron would then go and lose another electron, which would bring it to this. And this is what is referred to as the second ionization energy. This is like the first. And what might happen is this guy with a +2 charge would then maybe lose another electron, and that would be the third ionization energy. Is it easier to remove the first electron or say the last electron? Which one's easier? It is actually much easier to remove the very first electron because you're neutral at that point. And when you lose an electron, right, you become more positive. Also, what happens to the size of that ion? Does it get larger or smaller than the neutral guy? Gets smaller, right? The electron cloud shrinks, right? So the guy with the positive charge is smaller, which means now all your remaining electrons are now closer to the nucleus, right? So they're going to be held a little tighter, which means it's going to take a lot more energy to remove that. So that is the general trend that we actually see on this chart. And this chart is the first, second, third, up through 7, it looks like, ionization energies. And again, each of those represents basically 1 electron being removed from an atom. And we do see, if we look just, for example, from magnesium, First ionization energy is 735. Then it kind of doubles to 1440. And then as we try to remove the third electron, it goes up by almost like 7-fold. So a lot more energy required to do that. When we look at something like magnesium and we write the electron configuration, that's 1s2, 2s2, 2p6, a little 3s2. Magnesium, which is group number 2, has 2 valence electrons, which are the highest, most electrons. Everybody less than that is the core electrons, right? Those guys closer to the nucleus. So what happens as we remove the first one, it gets a little hard to remove the second one, but the second one will come off as well because it's a valence electron. When we then try to pull off that third one, we are now into our core electrons, which means not going to really happen in that case. And that's why magnesium, right, pretty much stops at a +2 charge, because after that you're pulling into the core electrons, which energy-wise is not effective to remove it at that point. And that's what we see here. That's why sodium, for example, only loses 1 electron, because you need like 10 times the amount of energy to try to rip off the second electron. And the second electron in sodium is actually its core electron, right? Because it only has 1 valence electron. So that's why certain things will make certain types of charges and only those types of charges. And that's the general trend that we see. Basically, our first ionization energy is usually less than a second. Second is usually less than a third, and it keeps increasing as you go from first ionization to second to third, and you continue to remove electrons. Any questions on that there? So here's a bunch of information. Clearly, you should know everything. No, I'm just kidding. But this is our first row as well. We talked about electron configuration, also size. I think we talked about the other day as well, and effective nuclear charge. Again, size decreases as you go to the right. You're also obviously building out more protons, which can give you a higher positive charge, going to bring everything in closer, which means the overall size of that guy will decrease. Here's our ionization energy in electron volts, which is a different unit. Our common sort of oxidation states, which is our +3s and +2s. We also see a slightly increase in the density as you go to the right as well. Here's our first versus third ionization energy. And again, you can see as you jump to that third ionization energy, trying to remove the third electron, much more energy is required to do so. Here's another graph in case you didn't like that first one that shows the second one as well. And again, the first to the second to the third increasing in terms of energy required to remove those electrons. Now, electron affinity is different than electronegativity. Electron affinity is actually the energy change that occurs when an atom actually gains an electron. And when somebody gains an electron, basically when you talk about electron affinity, you're talking about anion formation, basically, because as they gain an electron, they obviously become negatively charged. And in general, electron affinity does follow kind of similar to some other patterns. It does increase as you go to the right and up, and decreases generally as you go down. Is it perfect? It's really not. And we see that actually in group 7 here. It increases as you go up group 7, but when you kind of get to fluorine, it drops back down a little bit. So it's not like a perfect sort of pattern, but that is the general pattern that you see, a general increase as you go up and to the right, and a decrease as you go down and to the left. This obviously should not be confused with electronegativity, right? Electronegativity is the ability of an atom to bring electrons towards itself. It does sort of follow a very similar pattern on the periodic table, increases as you go up and to the right, decreases as you go down to the left. Most electronegative element starts with an F. Fluorine is the most electronegative element you could have. Can't go any further up to the right, other than the noble gases, but noble gases are chemically inert. Yeah, they actually have 0 electronegativity values because they don't really want anybody to come near them because they're happy with the electrons that they have, basically. All right, another table of some properties there. This is the relative reducing abilities of that first row transition metals, and what we see is greater reducing ability coming up here, right? Which means that the guy at the top here is greater being oxidized, right? So if you're a greater reducing agent, you will be oxidized. Now you maybe look at those potentials, and that one is more positive, which means it should be the one that is being reduced. But these are not standard reduction potentials. These are oxidation reactions. It's the opposite, right? So these are all oxidation reactions, sometimes referred to as SOP, which means if we turned all these guys into a SRP value like we're normally used to, right? We would change the sign on everybody, right? As we would reverse the reaction, which means this guy down here would technically be the cathode, right? And the one that would be reduced, and that would have the less reducing ability, which means it's more of an oxidizing agent, right? On that way. So if you turn this into an SRP, you would change the sign on all those, and that will correlate to what we talked about, obviously, with standard reduction potential. All right. This is what the first row transition metals look like in case you need to pick them out on the lineup. They look like that. That's our penny right there. All right. Save. I know it's like 5 days left. I'm gonna go with it. All right. So colors that you typically see in some of these transition metals, which if we did qualitative analysis type experiments like we used to, these might be helpful for you. But depending on sort of who they hook up with, they will have some distinctive colors, and based on their color and what they're hooked up with in terms of their oxidation state. All right. Any questions on transition metals? Yes. Okay. So again, we kind of went through that to review transition metals because, as I mentioned, it really is the major part of what are in these sort of complex ions, which is what we're going to really focus in on for the rest of this chapter, complex ions and coordination chemistry. So a coordination compound, you could kind of think of it like an ionic compound. And when you think of an ionic compound, there's like a positive guy, right? And a negative guy. And in a coordination compound, there typically is also a positive guy and a negative guy. There is the complex ion, which has a metal in the middle, and it's bonded to one or more molecules or ions, which, as we talked about, I think maybe the other day, those are ligands is what they are referred to, and those are our Lewis bases. And again, our Lewis bases are things that can do what again? Yeah, it should donate a pair of electrons, right? So as we talked about the other day, these ligands are able to donate a pair of electrons. And what makes something sort of a good ligand is typically they need like a non-bonding pair of electrons. And in that situation, for example, like water or ammonia, also being polar is very helpful for it to allow it to sort of donate away those electrons. Also, ions that are anions, which are negatively charged. Again, typically the way they become negatively charged is that they have gained electrons to begin with, which means, frankly, they have electrons they could give away themselves because they have already gained electrons. So kind of polar guys that have non-bonding electrons on sort of an electronegative sort of atom, and guys that are negatively charged to begin with typically make pretty good Lewis bases or ligands. Lewis acids, as we talked about, which is really sort of the metals role here. This guy in the middle, right, has a positive charge, which means much like a Lewis acid, it is electron deficient, which means it's willing to accept those electrons that are going to be given to them by the ligands. And that's why when we look at sort of a complex ion sort of situation, we oftentimes look at it more like a Lewis acid base situation that's happening where electrons are being donated, electrons are being accepted in this situation. And again, that sort of metal that has a pretty good positive charge, as usually what you'll find in the middle there, which is our transition metals like +2s, 3s, kind of 4s, whatever it may be. And that's because they're very deficient. And so they act as really good Lewis acids for those guys that want to give away their electrons that are going to be those Lewis bases that's going to come together. So when we make a coordination compound, it has two parts. It does have a complex ion, and it basically has a counter ion. And in the case of coordination compounds, either one of those things can have either charge. So what I mean by that is you could have a complex ion that is positively charged, and it would then have a counter ion that would be negatively charged. So very much like an ionic compound. When we put an ionic compound together, right, we want the overall charge to equal 0, right? And it's kind of a very similar sort of idea. Now, you could also have a complex ion that can be negatively charged overall, which means it would also have a counter ion, but it would actually be a positive counter ion in this case. So, your complex ion could either be positive or negative, and your counter ion could either be positive or negative, depending on what is needed. In the case of our ligands down here, again, that is pretty much where we're going to get that attachment and those electrons being donated here. And again, this guy with our negative charge, and obviously we have some non-bonding electrons happening on this guy as well. Now, when we take an atom that's going to be a ligand and it attaches to a metal, we sometimes talk about what is referred to as the coordination number. And the coordination number is the actual number of atoms that are directly attached to the metal in a complex ion. And the coordination number is not always necessarily how many of those ligands that you have there, but it is important the type of ligand that you have attaching in. Now, there are certain ligands where pretty much only one atom in that compound or molecule is going to basically attach to the metal. And those are what are sometimes referred to as being monodentate or unidentate, which means that basically they attach, you get like one attachment per molecule. So something like water, which will attach through the oxygen, will basically, if we had a metal, just going to basically attach there to the oxygen. And that's why water would be monodentate. Same thing with NH3. Again, if you had a positive metal, that is where you're going to get the attachment that's basically going to occur. You could also think about it, right, in terms of water, oxygen is more positive or negative? Oxygen is more negative, right, because of the polarness of it. Same thing with really the nitrogen in that case. It's actually more negative in that case. So again, that positive negative attraction between the metal that's positive and really kind of the negative side of that guy is going to attach. So if we had a metal, and then we put like, 6 waters attached to it, the coordination number here would be 6, because basically there would be 6 oxygens attached. Each of those oxygens would be water. I won't draw the rest of the water, but 1, 2, 3, 4, 5, 6. The rest of that obviously is waters, and then you would have those 6 oxygens being attached into it. Now, some ligands actually attach in multiple places per molecule of the ligand, and you kind of get like a 2-for-1 action here, and that's what happens when we have ones that are considered bidentate. And bidentate basically means that it can attach 2 places per 1 molecule of the ligand. Ethylendyl sounds very organic-y. Also abbreviated with as an EN, and that's a very common abbreviation that you'll see for ethylendyl. They will actually use that abbreviation both in the formula and actually when you kind of draw it as well. So they'll sometimes use it in both places. Just to show you ethylendyl, I'm going to give it the old college try here. It looks maybe something like this, maybe something like this, maybe something like that. And it's these nitrogens, which is basically a derivative of ammonia, that is able to, if you have a metal, and by the way, that's one molecule of En here. It will attach at both of those nitrogens, basically. So again, for every one molecule of that En, you will get basically 2 attachment points. So if you had a metal that, say, in a formula just said 2 of those guys, the coordination number here would actually be 4, would be the coordination number here. And that's because you technically would then have another molecule of it where those 2 nitrogens would attach, and now you have 1, 2, 3, and 4 atoms attached directly to the metal in the middle. So what happens, and I guess what I'm saying is sometimes people will look at the formula and go, oh, it's a 2, so the coordination number needs to be a 2, and it would be incorrect in this case because for every one of those guys, you get basically 2 attachment points. So you got to kind of double the coordination number for each attachment that you get. Any questions on it? Say again. The coordination, I can't hear your last part, I'm sorry. So it's basically figured out by how many atoms are directly attached to the metal. And it's based on whether it's a monodentate, bidentate type of ligand. And in the case of water, for example, water will only attach to the metal through the oxygen. So for every one water molecule that you have attached there as a ligand, you basically get 1 coordination number, basically. So if you have 6 of them attached, the coordination number would be 6. And that's because all 6 of the oxygens in each of those water molecules is basically what's attaching, which is what we see here. If these were all the water molecules, right? Basically 1, 2, 3, 4, 5, and 6 oxygens are directly attached to it. When we go to this guy, even though it says we only have 2 molecules of the ethylenediamine, each molecule of that has the ability to attach directly to the metal in 2 different locations. So that's 1 attachment, which gives us like a coordination number. That would be our second sort of attachment, which gets us to a coordination number 2. And both of those attachments come from the same molecule. But now we have 2 of those molecules, which means we have 1 more attachment here, which gets us to a coordination number 3, and 1 more here, which gets us to a coordination number of 4 in that case. So it does depend on the type of ligand that's there and really how many sort of attachments it could do per molecule of it. And it's not always just the kind of subscript that you see in the formula next to the ligands. Another very common bidentate ligand that we come across is our friend C2O42-, that's oxalate. And if you draw oxalate, it looks something like this. I think it looks something like this, maybe. Past chemistry once. Only once. There we go. We'll do that. So that is oxalate there if you draw it up. And in this case, if you had to take a guess which oxygens are going to attach, it is the guys that are really where the negative charges are, right? So they got those electrons. So for every molecule of oxalate, if you had a metal, it could attach through that oxygen and also attach through that oxygen, which means much like ethylenediamine, you will get a 2-for-1 type of deal on that. So you'll get 2 attachments for every 1 molecule, basically, of the oxalate. So that's another very common one that happens in a lot of complex ions that you have to double it. There's even some ligands that can attach in a lot of places. So 3 or more are sometimes referred to as being polydentate. And EDTA is ethylenediamine tetraacetic acid. It attaches in 6 different locations. So for every 1 molecule of that EDTA, basically there's 6 places where it will gobble up a metal. And that's why, as we'll see in a second, EDTA, for example, and some of these guys that could sort of bind in multiple places or sometimes used as chelating agents for metals because basically they gobble them up. And sometimes on ingredient labels, you can see something that says like EDTA because it's used to sort of gobble up some metals and stuff like that as you do things. All right. So how do we know sort of how many ligands may attach to a metal. And there's no very vast rule on it other than, sort of the larger the positive charge, the more sort of electron deficient it is, which means it's going to allow a lot more of those Lewis bases to sort of bind in. And kind of the smaller the positive charge, you'll usually get a little bit less of those ligands that will sort of attach in. So typically guys that have +1 charges, as you can see there on the left, is usually kind of 2 guys that will attach in, occasionally 4. When you get to kind of +2 type charges like we have in the middle, 4 and 6 are very common sort of coordination numbers that we see. And if you have kind of a +3 charge, again, more on the higher side, 6 guys are able to kind of get in there, except for gold, which usually will kind of hang out with 4 things sort of attached to it. So sort of roughly pattern is, kind of the larger the positive charge, you can probably get more ligands to sort of attach to it. Again, because we just think about it as a little bit more electron deficient than something with a smaller positive charge. So there's ethyl endyl diamine, and this is the EDTA molecule, as I was talking about a second ago. And as you can see here, it could attach in one spot there, through the nitrogen there, which is 2, through that nitrogen, which is 3, that oxygen, that's 4, that oxygen is 5, and that oxygen, which is 6. So that is one giant molecule of EDTA, and it basically can just trap that metal really well. It will basically go right around it. And again, that's why it's sometimes referred to as a chelating agent, because it could grab it in multiple locations. Which sometimes this is what you want to sort of get rid of it, right? Or maybe trap it so it won't go anywhere else. So here's a table, and you have a similar one in your book of some common ligands. Again, monodentate ones, very common ones that we do come across: water, ammonia, nitrite, cyanide, thiocyanate, hydroxide. And then our halogens, like, our chlorides or bromides, those guys are very common monodentate type ones. Again, the 2 kind of popular sort of bidentate ones, the ethyl endyl diamine, which is the EN, and the oxalate are very common. There's also this guy, which actually will attach in 3 places. This is diethyl triamine. It basically will attach 1, 2, and 3 places at the nitrogen is where it's able to do so. And then this is our EDTA molecule, which, by the way, has an overall charge of perhaps a -4 type of situation going on there. And again, at those places is where those things will attach. All right. So let's start with what is the oxidation number of the metal in each of these coordination compounds. And by the way, typically speaking, the complex ion a lot of times is written in the brackets. So the complex ion is typically written in the brackets. So why don't you take a moment here and figure out the oxidation state of the metal that's in the complex ion part here for each of these guys. Here, so we got something, okay. AuOH4. All right, so in this case, in the brackets here is going to be our complex ion. This then would be our counter ion. And if we look at it here, we have hydroxide, which is a -1, right? And there's 4 of them, which means that's like a -4 happening there. On the outside there, we have potassium, which is +1. That means that our gold here would have to be +3. Yeah, so the oxidation state of our gold would be +3. That gets us to 0 in this case, yeah. If we look at our second one here, same sort of approach. We have NH3, which has what type of charge? is 0, right? It's not NH4 plus, so that's NH3, which would be 0. Our NO3 is nitrate, which is -1. Yeah. And there's 3 of them, which gives us a -3, which means in this case, the chromium here also needs to be +3 to balance it out. Yeah. Any questions on that there? This again would be our complex ion. This would be our counter ion in this case, right? So if I took just the complex ion parts by itself, what type of charge would the complex ion part have overall? Yeah, so that's +3, that's -1, which gives us a -4, which means overall, my complex ion is -1 charge. This is a -1 charge complex ion, which means my complex ion in this case is negatively charged. Potassium is positively charged as my counter ion, and that is like an ionic compound, right? +1, -1 gives us 0 when we put it together in this particular case. That is also how coordination compounds are written, just like ionic compounds, positive guy followed by the negative guy. Yes. So it's always positive to negative, just like an ionic compound. That is why when we look at this complex ion on this side, what is the overall charge of the complex ion on this side? This is 0, and this was +3 we determined, which means the complex ion here actually has a overall +3 charge. That is why when we look at our counter ion in this case, it is nitrate, which is -1, right? But we don't need just one of them. We actually need 3 of them, right? To get to a -3 to balance out that +3 charge that's in the complex ion. In this case, our complex ion is positive and it comes first in the formula, right? Positive first, negative second in terms of its counter ion. So again, always positive and negative. Again, just like a traditional sort of ionic compound. Question on that. So both of these demonstrate what we were talking about earlier. You could have a complex ion that's positive overall charge. You could also have a complex ion that's negative overall charge. And you can also obviously have the corresponding counter ion that's going to be either positive or negative, depending on your complex ion. Any questions on that there? Okay. So then let us talk about the fun part of the day, which is naming. Yes, I know you thought like, have I learned all the naming I should ever possibly know? The answer is no, you have not. So let us talk about this naming. Let's talk about naming coordination compounds. So as we've been talking about, as we just saw in those last ones, we always want to go the cation first and the anion, so always positive, negative. And that's usually both in name and formula is how you want to go about doing that. When you have a complex ion, so when you're naming sort of the complex ion part of the coordination compound, we always go with the ligands that are named first in alphabetical order. And that is first in alphabetical order, regardless of any prefix that may be used in the name. So whatever the letter of the actual ligand is, that's the alphabetical order you want to go by. And you always name the metal last in that part of the name. So as you're naming the complex ion part, you should always start with the ligands in alphabetical order, followed by the name of the metal. And as we'll talk about, we also use the Roman numeral as well to use that for the name of the metal. Any type of anionic ligand typically will end with the letter O, so those are negative guys. Some neutral ligands will also be called by the name of the molecule. There are some exceptions, like water is known as aqua, and some books use aqua. Okay, CO is carbonyl. NH3 is amine. So some of these names are used instead of obviously the normal name of it. Now, if you do have several of the same ligands that are present, We do use some Greek prefixes, which is di, tri, tetra, penta, and hexa. So these are kind of normal things. That is 2, right? 3, tetra is 4, penta is 5, hexa is 6 in this particular case. Now, the thing that everybody else loves, which is if the ligand already has one of those prefixes in its actual name, then we actually roll to some other prefixes, and we use bis for 2, tris for 3, and tetrachus for 4. So I don't know what they were thinking when they made these things up, but there we go. We also, which is a little different than some of the regular nomenclature that you might be used to when you talk maybe about type 2 sort of naming, we do use a Roman numeral to indicate the charge on the metal that's in the complex ion. And we still actually use the Roman numeral on some elements that we normally don't do in normal naming. So things like silver, which has a positive charge, 1 charge, and a fixed charge, we still do put the actual Roman numeral 1 in there. So on those things like zinc and stuff like that, where we normally and sort of normal nomenclature don't include the Roman numeral, we still include the Roman numeral. Also, a weird situation that can occur in a situation of these type of complex ions or coordination compounds is you could end up with a metal that has a 0 charge, and you would put 0. Obviously, it wouldn't be a Roman numeral, but you would include the 0 in terms of the naming part of it as well. So it is possible to end up with a certain situation a 0 in terms of the charge on your metal, and you would obviously be 0 and include it in there as well. Now, if all these fun rules were not enough, the last rule is if the complex ion is actually negative, which is an anion, then you actually roll with kind of like the old school name for all the elements that end in 8. So instead of iron, it becomes ferrate. Instead of copper, it becomes cuprate, plumate, all those kind of older names that maybe you learned when or saw when maybe you're talking about like Roman numerals and not using Roman numerals. So we use those sort of older names. So let's take a look at some of these things here. Here's a table, and again, you have similar ones in your book of some of these neutral molecules and some of the names that go with it. Again, aqua or aquo for water, amine, methylamine, carbonyl, and then our halogens are sort of named very much like how they're named in sort of organic chemistry. So fluorine's a fluoral, a chloral, a bromo, or iodo. Hydroxo for hydroxide, cyano for cyanide are some of those names. And here's those sort of maybe older school type names or origin names for the metals. And again, these would be the names that you would use. And typically you kind of ended in 8 if the complex ion part is negative. So again, instead of iron, it'd be ferrate. Instead of copper, it'd be cuprate. And stannate for tin and so forth. And here's a few other ones on this table here. You got carbonate, that's carbonato, and you got oxalate, which is oxalato. I feel like I'm ordering some coffee right now. I'll take a carbonato with an oxalato and, easy on the aqua, I don't want all that stuff. So, we got ethyl endyl diamine. Again, in terms of naming the ethyl endyl diamine, that was the one we saw earlier. They do use the EN abbreviation a lot, again, in the name. And also in like the molecular formula, when you kind of put the formula together, they use that in both cases. This is EDTA down here, which as you can see is, big part of the name, right? There it is. That'd be like the extra credit question, spell EDTA, I suppose. So let's take a look at maybe the two that we were kind of taking a look at here. All right, so let's take a look first at this guy here and see how we would perhaps go about naming this guy. So first off, we will perhaps start with the complex ion part. So we're going to go with our ligands here. And again, if we look, we have our with maybe on this one here. We have our hydroxo, right, for our hydroxide. We also saw on that one that our complex ion is negative, and it was gold that was in there, right? So we're going to want to go with arurate in terms of the name. So let's go back to that guy there. So we have 4, right? And 4 is tetra hydroxo arurate Roman numeral 3. So this would be the complex ion part of the name. Again, ligands first, name of the metal, and then Roman numeral at the end. Now, the counter ion, good news is frankly just named like it normally would be. So if you had KCl, you would call this potassium chloride, right? So this would just be potassium. Yeah. So that is potassium tetrahydroxo arurate 3 in this case. Fun with naming, I think. Yeah. All right, why don't you give this guy a go? What would be the name of? Okay, let's take a look. So we're gonna go with this guy here. All right, so we did a lot of the preliminary work already, figuring out charges and all those things, which obviously, if you were just going to name these guys, is kind of what you want to do, right? So you could get the name correct. So here we're going to start with the complex ion part, and our ligands is ammonia, and there are 6 of them, so that's a little hexamine. And that takes care of this part of it. We will know that the complex ion here is positive, which means we could just use the regular name of our chromium, so we don't have to use the other name. So that would be chromium. We also figured out that it is a +3 charge and +3 here. So this is really the complex ion part of the name. Once again, ligands first in alphabetical order, and metal name comes at the end of the complex ion part with the Roman numeral. Earlier, I was talking about alphabetical in terms of the name and not the prefix. So if we were looking at, say, something like these 2 guys, say we were combining the 2, we would look at H here in terms of alphabetical order, not the T for the prefix. And here we would look at the A for the alphabetical order, not the other H that is there. So you would ignore the prefix if you have more than one type of ligand that is there. At that point, we have a bunch of nitrates, so it is just nitrate. Yeah. And that is very similar to how if you had something like this, you would call this calcium nitrate, regardless of how many you have. So you pretty much just use the name of it. For the most part, the counter ion is pretty much just the name of it, unless it is obviously the negative counter ion, like something like, say like Cl at the end, right? It would be chloride. So you would name it kind of like a normal anion ID at the end of it. If it's a polyatomic ion, you just use the whole name of it. Question on that name there. Now, if I wanted to just name the complex ion by itself, without the counter ion that's there, let's just say we wanted to just name, what is the name of this complex ion? It pretty much would be just this part of the name, and you would put an ion at the end, and that would be the name of just the ion by itself. And same thing for this guy. If we wanted just to name the ion part of this guy, we would drop off the nitrate and just use the front part here and put ion at the end of that name as well. Yeah. Any questions on that there? All right, then let's do some more fun naming here. All right, so why don't we do this one here, see what you come up with. It might be a little different than what you have on the paper. You can get this one. In this case, I actually know just from looking at it that my complex ion is negative, and I know that because it comes second in the formula, right? Which means it should be negative. My counter ion, which would be this guy, should be positive. Now, if we look at this, oxalate is -2. and there's 3 of them, which means that we will have a -6 in this case, and we have +1 for the potassium, and there's 3 of them, which means it's +3. So the chromium here will be +3 in that case, yeah, to balance it out. There's not any question on that there. All right, so knowing that it is a negative complex ion, that means instead of chromium, we do need to use the ATE version of it, which would be chromate. We also now know it's a Roman numeral 3. We have 3 of the oxalate, which again, if we look here for oxalate, is our oxalato. So that's going to be a trioxalato, and that's going to be a chromate Roman numeral 3. And now we have just the counter ion to name, which again doesn't matter. We have more than one of them. It's just going to be potassium here. Now, oxalato is, or oxalate is kind of a weird one. They do kind of sometimes historically will use that tris type of nomenclature here. And so you may actually see it like this as well. And oxalato is kind of like one of the only ones that maybe that sort of occurs where you can kind of do it both ways, and you kind of see it both ways in there. Now, I think on your paper, you might have had a water, some type of water there. Well, how many waters was it? 3, maybe? 3 waters, yeah. And when you have a formula written like that, which I'm not even sure on the handout was written, it had that dot in the right spot, but that's a hydrate, right? And hydrates are pretty much waters, right, that have kind of crystallized with things. And to name water in a hydrate, we just call it hydrate, and we do use a prefix for how many there would be. So if you did attach the water, you would then have tri for the 3 waters, and hydrate would be the last part of it in this particular case. Yeah. Yeah, so that charge on chromium would be its oxidation state in this case, yeah. By the way, the coordination number here would be how much? It would be 6 in this case, as oxalate is a bidentate one, which means for every oxalate you get 2 attachment points. So 2 times 3 is 6. So again, it's not always, as I mentioned earlier, going to be kind of that number. It will be if it's monodentate, but if it's a bidentate ligand, then obviously you need to adjust it for that. Speaking of that, we'll go back to our other ones here. Our coordination number for this guy would be, coordination number for that one would be 4, yeah. And that's because OH is OH minus, which is monodentate. So for every one of them, it binds in one place. So the coordination number would be 4. Coordination number on this guy would be, coordination on this guy would actually be 6 in this case. And that's because ammonia, which is this guy, every ammonia will only bind through the nitrogen. So you got 6 of them, 6 of those nitrogens will bind it. Yeah. Question on that there. All right, so let's try a few more here just to make sure. All right, so here's also a list of some other metal names if they are negative on the right there, which might come in handy as well. So top one there, we're looking for the, so we're getting to the end here. We'll start the first one. So once again here, just by the location of the complex ion, I do know it's going to be positive, which means I could use just the regular name of the metal. This would obviously be my counter ion right there, which should be negative. So here we'll just start with the pieces. We have 4 waters. So 4 is tetra, and then water is aqua or aqua, whichever way you want to do it, it's okay. We also have 2 of the chlorides here, and that's a dichloral situation. And obviously here we have chromium, which we might want to figure out the charge on it. So water is 0. Each chloride is -1, and there's 2 of them, which means there's a -2 happening there. We also have another -1 on the outside there, right? That's a total of -3. So the metal here is going to be +3. I know we hit a lot of +3s. They will not always be +3, but in this case, we do have +3 in this case. The last part here will be chromium-3. Now, alphabetical, which one should come first? Yeah, it is the water here should come first. Again, we're comparing the A to the C. Again, without the prefix is what we're looking at. So this would be tetra aquo. I get that Q, aquo, dichloral. Again, we're gonna go with chromium and our Roman numeral 3. So that's the complex ion part. Once again, the metal comes at the end of the complex ion part, not necessarily the end of the name in this case, right? But just the end of the complex ion part of the name. And then we have just the Cl, which will be chloride, like a normal anion, IDE. Any questions on that one there? Now, looking at the second one, we want to write is formula. So we have tris ethyl endyl diamine. And as I was mentioning earlier, the reason they do use tris here is because in the actual name of the ligand, there is a prefix. So that's the di prefix. So that is why they're using the tris here, because the actual ligand itself has a prefix in its name. But regardless, tris means 3, and that ethyl endyl diamine is the En, and you can just do that if you like. Cobalt has a +2 charge in this case, I think it is, because of the Roman numeral. So putting together really the complex ion part, which obviously would be this part of it, and I know that's the complex ion part because the metal is at the end of it, right, with the Roman numeral, so that's definitely the complex ion. We could put our little bracket, we'll do a CO, and we'll do an En and a 3. Now, we do know sulfate here is going to be our counter ion, which is this guy. What would be the actual charge on this complex ion if I just had the complex ion by itself? The overall charge here would be, this En is 0, right? And this guy we determined there is +2, which means this overall guy is +2. That's important because that tells me how many of these guys do I need? Just one, right? Because it's -2. So we would just need one to kind of balance that out, which would give us COEN3 SO4. Yeah. Any questions on that? Yeah. Good question. What would the coordination number of the first one be? I scribbled a lot over that. So that's coordination number would be what? Well, it would be a coordination number of 6. Yes, because basically you have a chromium that has 1 water attached, 2 waters attached, 3 waters attached, 4 waters attached, and you also have 2 Cls attached, right? So that's 1 atom, 2 atoms, 3 atoms, 4 atoms, 5, and 6 altogether. Yeah. The other one would be a coordination number of 6 as well. So that was the nitrogen one I drew earlier. So that one, for every molecule of it, will attach between the 2 nitrogens. So you get 2 for 1. And that, since there's 3 of them, that would give you a coordination number of 6. Other questions? All right, lay it up.